different types of circuits. Now, up till now, you've been doing all battery circuits. So if you look at this circuit here, it looks rather complex, right? All those little squiggly lines are resistors. But this right here is the battery. That's where all the electrical potential difference comes from, the chemical reactions in there. This side's positive, that side's negative. Now, if we trace the electricity's direction, usually we talk about going positive to negative. So there's lots of different ways this could get back to where it started. It could go this way, could go that way, could go that way, could go that way, could go, whoa, that way, could go, whoa, that way. So what is that? That's 1, 2, 3, 4, 5, 6 different paths it could take to get back to the battery. And in fact, electrons actually take all those paths because electrons repel each other. They want to have as few electrons in each area as they can. Not that they want anything because they're not alive, but that means there's 6 paths that they can go on from one side of the battery back to the other. Those are parallel paths. Now, this is a little more interesting. This is the kind of circuit that there is in a house. So you have a place where there's high electrical potential. That might be the little box that's out on a light pole, and you got wires going along it. That might be going down into your house. That's a terrible house, but oh well. Here we'll give it some windows and a door. So it goes down into your house. Now, outside of your house, where the meter box is, there is also a spike in the ground. And the top of that spike is connected to your house, and that's this. This is the ground spike. So one way to think about this is electricity going in here and all the way down to the ground spike, or maybe in here and all the way down to the ground spike. There's lots of different possible ways it could get there. All those are different possible parallel paths to the ground. But in general, electricity starts out here, ends up down here. But you got to realize with houses, it's actually a little more complicated. We're not going to have time to talk about it this year, but the electricity actually goes back and forth and back and forth and back and forth. That's what's called an alternating current. Batteries, for the most part, make direct current. The electrons actually go back and forth, back and forth, back and forth really fast for a house. That's called alternating current. All right. So lots of different parallel paths to the ground. Question is, how do we figure out how hard those paths are for the electrons to follow? So there's a thing called equivalent resistance. Let's work a few of these problems together. You remember, hopefully, V equals IR, or R equals V divided by I, or I equals V divided by R. So that is Ohm's law. And these resistors follow Ohm's law, but all of them act together. So let's see how you find what's called the equivalent resistance. Let's start with number 3 here. So if you want to find the equivalent resistance of a series arrangement of resistors, you just add them up. So when you add those up, you're going to get 20 ohms. So these 3 resistors are like one resistor that was 20 ohms. So if you want to find the current through this circuit, you do I equals V divided by R. Voltage is 10 volts because it says that right there. And your resistance is 20 ohms. So that's going to be half of an amp. So half of an amp is going to be going through that circuit. Let's do another one, number 4 here. So for 4, that's going to be total resistance is 3 ohms plus 11 ohms plus 4 ohms. Total resistance is 18 ohms. Current is going to be voltage divided by resistance. So that's 6 volts over 18 ohms. That's 3/9, so a third. So 0.33 amps. Now you'll be doing more of these. Realize that all those electrons have to go through all those resistors because there's only one path. These are series circuits. Let's take a look at parallel circuits. Okay, here's some parallel circuits. 8 and 9 here. Now, parallel calculations are a little interesting because you actually have 1, 2, 3 paths to the ground. That actually makes it easier than having one resistor. Unlike series resistors where it's harder, this is actually easier. So let's calculate the total resistance for this. It's actually the inverse of the total resistance is equal to 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor, however many resistors you have. So 1 over 2 ohms plus 1 over 4 ohms plus 1 over 8 ohms. And you could do this with decimals, but real quick I'm going to, because I don't have a calculator handy, I'm going to change this into fractions. So that's 4 over 8 ohms plus 2 over 8 ohms plus 1 over 8 ohms. That's going to be 7 over 8 ohms. Cross multiply, that's 7 times R equal 8, or when you take the, you could just take the inverse too and say the total resistance is 7/8 of an ohm. You could also just do that with decimals and that would be fine too. So if I want to find the current, I equals V divided by R. Voltage is 10 volts divided by 7/8 of an ohm. That's going to be 80/7 of an amp. Let me pull out a calculator real quick and we'll figure out what that is. Could have done a calculator much earlier, as I said. There we go. 11.4 amps. Alrighty. A little bit over 10 amps because they're a little bit under 1 ohm of resistance. Same thing with 9 here. So if we're going to do 9, we'll do 1 over R total is 1 over 40 ohms plus 1 over 20 ohms. Let's do calculator this time. Divided by 40, that's 0.025 over ohms plus 0.05 over ohms. So add those together. 0.075, take the inverse. And you get a total resistance of 13.3 ohms. Now this should be smaller than that or that, and it is because you have more possible paths. It's like having more hallways to walk through. It's easier for all those electrons to get through if there's more paths. So the total resistance should be lower. Current is voltage divided by resistance. So that's 10 volts divided by 13.3 ohms. That's 0.75 amps. Hopefully those examples are helpful to you. Let me know when you have questions. Thank you.